In today's lecture, we're looking at floating-based systems, so systems which are not rigidly connected to the ground. And in this first video segment, we are discussing the kinematics, or the description of the motion of these floating-based systems. Now, the special thing about floating-based systems is, as the name already says, is that it has a floating base, so it's not rigidly connected to the ground. And in order to describe the motion of such a floating-based systems, we have to describe the motion of the system internally, so how the individual joints are moving, but we have to also describe how the base is moving with respect to inertial frame. So if I have to describe this through generalized coordinates, I have to first have generalized coordinates for the joints as for any other robot type, but then we have to also have generalized coordinates for the base here indexed with QB. And this QB, as we know, is describing a body which is moving in 3D space. So it must have a position, which is this QB position, and it must have a rotation. Now the position obviously lives in R3, while QB describes orientation, so it's in SO3. And that means this QB has a dimension which depends on the choice of parameterization. If you have Euler angles for rotation, we have here a 6-dimensional vector. If I use quaternions to describe the orientation, I can also have here a 7-dimensional vector. Now the question is, how do generalized velocities and acceleration then look like? What we could do is you could do directly time derivatives, q dots and q double dots, but the thing that is not very nice is that this would then depend on the choice of parameterization. So if I have a quaternion to parameterize my rotation or an Euler angle to parameterize my rotation, I get a generalized velocity which is different, and that shouldn't be the case. So what people typically are doing is that for the generalized velocity, which we indicate here with U, we have a linear velocity of the base, and we have a angular velocity of the base, and we have the joint velocity. So we have these three components, which then are unique, and they have 6 degrees of freedom, so 6 dimensions for describing velocity and angular velocity of the base, and then we have the number of joints for the nj q dots of the joint. And then if you do time derivative of that, if I take u dot, which are my accelerations, I have the linear acceleration of the base, I have the angular acceleration of the base, and I have the joint accelerations. Now, as you can see here, we have a index here which is b, so often the angular velocity of the base with respect to inertial frame is expressed in b frame. It doesn't have to be, but it's often done. And the reason for that is simply if I want to measure this, what I typically do is I put an IMU on the base, and that IMU directly measures the angular velocity of that body with respect to the inertial frame, but since the IMU is mounted on the body, the reference frame here is B. And as we know, there is a linear mapping between q dots, so time derivatives of parameterizations, and velocities. And these mapping matrices, its E matrices, have been derived for all the different parameterizations, for quaternions, for Euler angles, and so on and so forth. So that means we can now, for this complete matrix, which is composed of linear velocities, angular velocities, and joint level velocities, we can have a combined mapping matrix, which for the linear velocity of the base we have only identity, the same for the joint velocities, and then in between we have the mapping matrix which depends on the choice of parameterization for the rotation. So if I have a quaternion parameterization, this ER, just for recap, this ER for parameterizations is in R3 times 4. So we have a 4-dimensional q dot vector, while we have only a 3-dimensional u dot for this specific orientation of the base. Now, important thing is that while this should be clear for you, bear in mind that very often people just write q dot, but they mean u. So if you see a paper and people write the equations of motion of a floating base system, they very often just write q dot, but what they mean is u. And also in my formulation, I will not always be extremely strict with that. Just bear in mind when you're talking about floating base systems, you have to really know what the velocity, this u vector, is. Now, if we analyze the kinematics of these robots a little more in detail, what we can do is we can write the position of an arbitrary point on the robot, point Q, as this point Q as a position that is an offset, first going to the base and then going from the base to the Q. And this BQ is expressed in B, which means in order to sum these vectors up, we have to first do the transformation from B to I prime. Now what you see here in this formulation is nothing else than I'm interested in a point Q, for example the hand, and I know that this point Q has a simple offset from the base, this RBQ, which is a function of these joint coordinates, as long as I'm expressing it in B frame. And then I have an offset from the origin, this RIB. And this, of course, I can express in I frame, but then it's depending only on these base coordinates. And the sum of these things together is then this vector, this RIQ. So I have here this RIQ, which is composed of this RIB as a function of the base coordinates, a rotation matrix, which is also only depending on the base coordinates, and the offset vector between B and Q, which depends on the joint coordinates. Now we can analyze the velocity of this point. To do this, we simply do a time differentiation. So we do here a time differentiation, d dt. We know that the base velocity at the base position, time differentiated will give just the base velocity, and then we have the product rule, so c dot times r plus c times r dot. And now we know this c dot, this is somehow related to the cross product matrix of the omega vector. I just write this here for completeness, and all we have to do now is that we have to go in here, we take this c dot and we replace this one in here. By doing so, we can rewrite the whole this whole formulation the following way. So we have this one in here, and then we can change the order. So instead of writing omega cross r, we can write minus r cross omega. This is the move down here. So we change order of these two and put the minus sign here. And then we know that there is a linear dependency between r dot, which is equal to j times q dot. Now, if I have only a dependency on qj, so I have here qj, then I write here j qj. And bear in mind, this has also then a different dimension because this is only r and j. So it doesn't have the full length of all the q's, but only the length of the number of q's of the joint, so the number of joints that we're having here. And if I have this, I can rewrite this in matrix form. I can move out all these components, this component, this component, and this component, which I stack in U. I stack these ones in U, so I have this here, here, and here. And then I have identity for mapping the u's to base velocity. I have this minus c times the cross product matrix of r bq, which maps the omega of the b frame with respect to I and b. And we have a rotation matrix times the Jacobian, which was taken with respect to the joint coordinates, times the joint level velocities that map the joint level velocities to end effector velocities. And this together is now the generalized Jacobian of point Q that maps U to velocities. Now, floating-based systems can only move by being in contact with the environment. So that means contact constraints are a very important concept in all of that. What we have to do is we have to look at the contact point, which we indicate with C, and we know that this contact point is not allowed to move. So that means that the position of that point C with respect to inertial frame expressed in inertial frame must be constant. So its velocity and its acceleration is both equal to 0. So what we can do now is we can write this constraint as a function of generalized coordinates. So we know that the Jacobi times u is equal to the velocity at this point. So this r dot here, this one, must be 0. And we also know that the r double dot must be 0. So we have two constraints which are a function of u and a function of a couple of Jacobians if we are talking about velocity space, and of u dot and Jacobians if you're talking about acceleration space. We can then stack these constraints. So assume that we have multiple points that are in contact with the environment. We can simply stack them as we did before. We have a stacked Jacobian, a stacked contact Jacobian, which just has all the individual contact points in there, and we know that this Jacobian times u must be 0. Now, given these contact constraints, which for example tell us that these feet are not allowed to move, we of course can still move the system, so it doesn't constrain everything. And to see how the system can move while ensuring these contact constraints, what we have to look at is the null space projection matrix, so similar to what we did in the earlier kinematic sessions. So if I look at my contact point, RC, and I know that this contact point has 0 velocity, so RC equal to 0, we write this as JC times Q dot. We can then solve this for Q dot by taking the pseudo inversion, but then there is an additional component here, which is this null space projection matrix times this Q dot 0. That means I can modify my Q dot through this null space projection or in this null space, which does not violate these contact constraints that says my feet are not allowed to move. And we can do the same thing also on acceleration level. Here the only difference is that we have this coupling term J dot Q dot, but all the rest remains the same. We have the same null space projection matrix and the same dimensionality of this null space. So that means this system can now move without violating the contact constraints. For example, if I want to move this end effector here or the base here, what I can write is I can write now a task which says I want to move my end effector, which is JE times Q double dot plus J dot times Q dot, and this we want to move with a desired acceleration. Or I can do the same thing on velocity level, but we can only do this subject to that this higher level or these higher priority tasks, namely the contact tasks, are fulfilled and satisfied. And we know how to do this, namely which is to prioritize inverse differential kinematics on velocity or on acceleration level, and that gives us the joint level and the base motion of the system which ensures that this task is fulfilled as well as possible while not violating the contact constraint. And we are doing this here in the form of a very simple example as a quiz. We have here a wheeled system that can only drive in X direction, so a very simple setup. We have two generalized coordinates, Q, X, and Phi. And what we want you to do is we want you to identify the contact constraints by first looking at this point on the wheel, this point P, and identify the Jacobian at that point P, then write down the contact constraint, and then identify the possible null space motion for this system.